Daniel for and Jan for the invitation to speak at this new seminar series. I've decided on a topic that's related to that's related to this year the Nobel Prize in Physics that you will have all heard about, notably about it's related to the work by Roger Penrose on black holes, although not the work that he got the Nobel for. It's also, I should also mention these two other scientists who were awarded for their observational work on black holes, which helps us, or which is obviously confirming the reality of these objects and puts this talk into the middle of theoretical physics, not imaginary physics. Now, what is determinism? You will all know the quote by Laplace, or you will at some point heard that his name is often associated with this doctrine. Anyway, I found him having said on Wikipedia that in intelligence, which for one given instant would know all the forces and respective situation of the entities which compose it, if besides it were sufficiently vast to submit all these data to mathematical analysis, for it nothing would be uncertain and the future would be present to her eyes. It's very nicely put. Of course, we know from many viewpoints that certainly we are not this, our humankind is not going to be this entity capable of this kind of universal mathematical analysis, and probably for information theoretical reasons alone or thermodynamic reasons, such a being could not exist. But he didn't, in all likelihood, mean it all that seriously, and he just wanted to make the point.
And
now,
where is the end of the quotation? There was only the beginning of the quotation. I don't see that.
Sorry, I couldn't hear this.
Where is the end of the quotation symbol?
Oh, the quotation symbol ends after eyes, but presumably the quotation goes on. I'm sorry for this. Okay, now the PDE version is closer to mathematical physics. It's often verbally attributed to another famous Frenchman, Cauchy. And according to this viewpoint, it's a much more specific notion of determinism, which is the one that I will be using throughout this talk. And it says that the solution to a wave-like equation is determined by its initial data inside the so-called domain of dependence. So this is still not super precise because I haven't told you what a wave-like equation really is, but it's some sort of partial differential equation whose highest derivative part has the form of a wave operator. Now, I don't think this was the way in which Cauchy phrased this. I think this is this viewpoint emerged from later works, such as yet another French mathematician, Leray. I'm just showing Cauchy here because his name is then also associated with objects in and outside black holes that are somehow related to causality. Now came along general relativity somewhat later, and in general relativity, there are some immediate new issues with determinism, from now on understood as this property of wave-like equations. And somebody who has ever attended a class on general relativity knows that one can, even insisting on Einstein's equation, construct very easily this kind of absurd spacetimes wherein you take Minkowski space and you identify time and you obtain a kind of a cylinder where the time direction wraps around the cylinder. And then if you shine your light, if you shine a beam of light into the future, as shown, it will come back at you. And then obviously what you thought, according to your wave equation, was going to be empty space is now suddenly lit from the past by light emerging from the past. And so there is an obvious kind of time machine-like thing going on here. But these things are really just stupid, silly. Well, for all we know, they're just silly academic examples that Einstein equation somehow allows you to construct, but there is no way that we know of you could really manufacture such kind of a space-time from starting from some reasonable situation. But there are issues with determinism inside black holes, and that's a much more of an issue because black holes are not only possible, according to the gentleman, for example, that and lady that were awarded the Nobel Prize, but they're, as many relativists and physicists believe, are actually unavoidable and absolutely central. So this is now, if you have such kind of issues of causality inside black holes, that would be a much more serious issue. Now, let me build up to this story, but because you may not be relativists, and because I will be using a kind of a relativist way to draw space-times, I have to briefly introduce that. And the kind of picture language that is very common and that I will use throughout is that of Penrose or Penrose Carter diagrams. And so basically the way this works is by a conformal mapping. And because this would be most familiar to you, I thought I'm going to start with the conformal mapping of the two-sphere to two-dimensional Euclidean space, the stereographic projection, which you see here. I think I don't have to explain it, except perhaps that if in terms of geometry, in terms of the line element, what this mapping does, it is equivalent to decorating the round sphere metric with a so-called conformal factor. So this conformal factor is telling you that this point at infinity, at the North Pole, really a rather small distance on the sphere here is going to mean a huge distance on Euclidean space because the conformal factor here is 0 on the North Pole. So you map this one point to the point at infinity. You know this construction is also called the Riemann sphere. It's very well known. Okay, so having said that, I now want to come to a Lorenzian analog, and this is what I'll show next. If you just give me 1 second, I have to adjust something here on my computer. Sorry for the interruption. So now you will have had time to study this carefully executed drawing, which is supposed to be the Lorenzian analog of the stereographic projection. Now, the only difference is that instead of the Euclidean plane, I'm studying the Lorentzian plane, or Minkowski space, which has a minus here in front of the time part of the line element. And now the way to draw it is like this. Instead of the North Pole, you have this point here, and instead of the sphere, you have this kind of somewhat bizarre looking wrapped up handkerchief, and you have to bend the plane, the Lorentzian plane, in a kind of hyperbolic fashion. And then you see that you map any any point here on this high Lorentzian plane of Minkowski space to a point of this handkerchief. And the handkerchief is different from the sphere. The handkerchief has the points where its tips are joined, but then it also has a rim here and a rim part here, and all of these parts really correspond to infinity. And I once talked to Roger Penrose, how he came up with these Penrose diagrams, and he said, I mean, he didn't show me this drawing, but maybe that's what he thought about. He said he knew conformal transformation of the sphere, and so he asked himself what would be the Lorenzian analog, and this is kind of what it is. So the point is that infinity is kind of a more complicated thing, and it's better, I think, to draw it this way, where you take this handkerchief and you unwrap it and put it on the table. And now these 2 points here, left and right, were identified. There are what is called spatial infinity. Those would be the points that you can reach along a space-like trajectory, going all the way into the blue yonder. And then you have these other diagonal lines, which correspond to null infinity, they're called, which will be the final destiny of any light ray going past our future. And then you have these other points, I plus, I minus, which will be the destiny of material massive observers. So I plus is here, I minus there. So that's how you think about it. So just as an ordinary conformal transformation distorts distances but preserves angles, the Minkowskian analog preserves causal relations, in that light rays still go at 45 degrees, and time-like curves go at an angle of go kind of up the whiteboard, and spatial directions are kind of at an angle less than 45 degrees. So in this talk, we'll be talking about 4 dimensions. So you have to do something to go to 4 dimensions, but it's of a fairly trivial nature, or you can write the 4-dimensional line element in this way, that you introduce spherical polar coordinates, and then the angular coordinates go for the ride, and the time and radial coordinates just play the same role as t and y over here. And you just have now just a half of this picture, because the radius is positive. So the radius is positive. Okay, so from now on, I will draw these pictures, but I will draw them also in cases where we do not have Minkowski space, but where we have black hole spacetimes. And if you've had a course on general relativity, you will have heard about a special solution to the Einstein equations, which is the Schwarzschild black hole. The metric is written in similar spherical coordinates as just shown in this form, where there is just a small difference, really, that the coefficient of dt squared is not 1 or -1, but is this function, and likewise of dr squared. And now when you draw this diagram, which is kind of a more complicated business, because actually you need to make various analytic continuations of this thing first, but the end result is this picture. And this picture is telling you that you have this kind of diamond-shaped region here, which is kind of like this part here, except that there are these other null surfaces here, which are not infinity, but which are kind of other types of boundary of the space-time. And you see one feature here is that a light ray which goes at an angle of more than 45 degrees cannot go from inside into this diamond, and a diamond kind of represents the asymptotic region. So therefore this region here is called a black hole part of the space-time. and an observer which goes at an angle of less than more than 45 degrees A will inevitably strike this this place where really space-time ends and where you have a curvature singularity. So this would be not a good place to go, and if you did go, you would be you would not survive this, and you would fall into the singularity in finite time. I've also drawn something else, this kind of a shaded region, which is supposed to take into account the fact that a black hole will not be there forever since the dawns of time, but it will have formed in reality from a collapsing star. And as Oppenheimer and Snyders and other people showed many years ago, one can construct such more realistic, was one by Werner Israel and Eric Poisson, who looked at fluids in this kind of situation. And they kind of, well, it's a more complicated story to tell, but one also gets the impression really that these perturbations or these fields blow up at the Cauchy horizon. And so if you believe that, then determinism is restored in the sense that you may draw as a mathematician this nice diagram, but really this part up here, it doesn't exist. And really already here, there's the singularity. And there already you end your life. And there is no question what is after, because that's really the end of it. Now, I wouldn't be here if there wasn't a new development. And the new development, although you do not necessarily have to introduce a cosmological constant, it becomes most pronounced if you do so. So if you introduce into your space-time a positive cosmological constant, then again, you have a very similar solution wherein just this F is again slightly different. And it doesn't help to stare at this F, but you should look at the picture. And the picture is telling you now, okay, the infinity is a bit different, but still you have this region with this Cauchy horizon. And if Bob crosses it, he's not able to calculate if even he was what I don't know, I don't remember how Laplace said it, but an intelligence capable of submitting everything to an infinite analysis or something to this extent. Well, he couldn't predict what was there. Now, there is a new effect physically, and this new effect is the following. If you have this cosmological constant, then space outside the black hole wants to expand.
So sorry, Stefan, can I interrupt briefly?
Yes.
So there was a problem, and okay, this is a panic. So I sent an email about opening a new link, but I see that this link is working again, and people have rejoined. So can we perhaps pause 5 minutes in order to let more people to rejoin? I'm also going to send an email to everybody.
Okay, well, it says 32 participants here in my tab.
No. Yes, so we had a bit more before. Would you mind going back to where it stopped? And even if you go a bit quickly. And
yeah, okay, let me go back.
Thank you very much.
No problem. Okay, so there is a problem of indeterminism because even knowing everything, knowing everything initially, you won't know what's beyond the Cauchy horizon because fields evolve to a wave according to wave-like equations, and wave equations have a domain of dependence. And therefore, you can't know what's here. And point number two, realistic black holes have these regions. So it's in principle a problem. But Penrose said there is a blue shift because basically objects going in will cross after a finite time this surface, whereas objects staying outside will have an infinite amount of time. So there is an infinite discrepancy of of proper time. And this gives a rise to a blue shift or to an increase in frequency and therefore an increase of roughness of fields, which become so rough that they cause a flash of stress energy, according to him, as we cross the Cauchy horizon. Now, there is a competing effect, I was about to say, if you have a cosmological constant, because in the cosmological part of the space-time outside, space expands exponentially, so fields will be diluted very much. The amplitude will correspondingly go down exponentially, whereas the blue shift effect is an increase in the derivative. So there is a competing effect, and now it's not so clear anymore that the transverse derivative of the field diverges at the Cauchy horizon and helps us relegating this problem of determinism to the realm of quantum gravity, or whether maybe now the transverse derivative is rather regular. So I wasn't the first, or we weren't the first to look into this. Again, there have been papers, I think, studying seriously, starting with work by Mellor, Moss, and also Myers, by Brady, and I think even already Chandrasekhar and Hartle did something. I have to admit, I'm not quite sure exactly what they did, but Mellor and Moss certainly looked at this problem, but they had a kind of not so clear story, and so they themselves reinterpreted their calculations a few times. And so this has been looked at then more recently by various people, including the Cambridge people and Cardoso and his company and so on in physics, but also it has stirred a lot of interest among top class mathematicians working in the theory of partial differential equations, among which certainly Christodoulou must be named for having studied this spherically symmetric type scenario, but then more recently Defermos and Luc, Spirsky, various people, and in particular Hinz and Vagi looked at this problem. So what is the problem? So you have a wave equation on this kind of space-time, and you start out with some very nice initial data here. And you look at how this field phi, which is you could even take a linear wave equation, but if you're more courageous, you could also look at the full Einstein equation even. But already at the linear level, this is basically a very interesting problem. And they said, they came ultimately to the conclusion that the field here is at least of a certain Sobolev class. Now, this is a mathematical physics seminar, so I assume Sobolev spaces. The Sobolev index is sort of how many fractional derivatives you're allowed to take and still be in L2. And the interesting part is what this index is. And that's written here. So the index is 1/2 plus something. And the something is a quotient. And that quotient represents this competing effect I was talking about. More specifically, there is an alpha, which is the exponential decay rate due to the cosmological expansion, or more technically, it's some gap in the resonances of some associated scattering problem, which I don't want to describe here, but they're called quasi-normal frequencies. So there is a certain gap, and the width of this gap, just as in atomic physics, is related to how quickly this kind of thing decays. And then there is a kappa minus, which is called the surface gravity. Now I'm just also not going to explain what it really is, but there is the blue shift effect, which is kind of a local thing. And then there is this decay effect from the cosmological constant. And they compete, and the competition is seen in the differentiability class now of this solution. And so you see the wider the spectral gap, so the faster the decay outside, the better the Sobolev space. And on the other hand, the smaller the surface gravity, so the more violent the blue shift. Sorry, the other way. So the bigger the surface gravity or the temperature of the black hole, as we say, the smaller is the Sobolev index, and therefore the less regular this thing. So if you are very rough, you could say, if this is to translate this into some polynomial, inverse polynomial decay, then this means that the flash of stress energy as you cross the Cauchy horizon is this V minus 2 inverse that Penrose said, but then it's a little better by 2 beta. And the 2 beta can actually be very large according to numerical calculation. So what you have to calculate numerically in this problem is the spectral gap, because you have to solve some sort of Schrödinger equation. And the Schrödinger equation is not of a type where you can just do it. It's not of an integrable model type. So you have, there's some numerics you can do here, but it's without, there's no question that, for example, you can vary the parameters such that it becomes bigger than a half. And then you see your solution is in H1, so it has a square integrable stress tensor. And this means basically that the flash at the Cauchy horizon, this singularity, is very weak. And therefore, it means that the issue of indeterminism is back. So the story is again like this. So first, Penrose said, well, first you think there is a problem. Then Penrose said, well, the blue shift effect, perhaps there is no problem because fields are very singular here. So in particular, the metric in the full nonlinear Einstein equation is very irregular. Practically the space-time ends here. But then serious mathematicians looked at it again, and also serious theoretical physicists, and said that, well, the singularity actually is quite weak. And in fact, you don't really need a cosmological constant. It just makes this more pronounced. And Fermos and Luc, for example, showed that the field is even without a cosmological constant is continuous. And so the solution it's still a singularity, but from the viewpoint of PDE, it's a singularity where you can still continue the solution as a weak solution. So this is kind of good enough in some sense. So there is a problem, really, and it's not an academic problem, and you have to decide what you're going to do about it. And so that's where we started. So if you have a very weak singularity, then the classical fields don't do much at the Cauchy horizon. And so you can ask whether perhaps quantum fluctuations of the fields are going to in any way drastically change this. And then this has been investigated in work by us. And there was, again, these quantum fluctuations on black hole spacetimes have previously certainly been analyzed by, for example, Ori et al. And by these people in a kind of very special case that as I explained, is a bit pathological. But they have not been analyzed really at the Cauchy horizon. And that's what we did. So you have to go to quantum field theory really to make this work, or to phrase the question. Now, I can't really go into this in too much detail, but what you have to say is that on this space-time, the field isn't classical, but it's a quantum field. And so what you really know are the correlation functions of this quantum field in some state. And the quantum state is what is the analog of the initial condition. So if you think about a Schrödinger equation, you would fix the quantum state initially here, and then you would solve the Schrödinger equation. You can think about it this way, except that we like to think more in the Heisenberg picture, where the state is fixed, and the fields, the observables, evolve in time. And we're thinking of the observables not in the sort of Hamiltonian way, but it's better here, obviously, to think of a covariant way, and therefore the observables are just like the classical fields, functions of the space-time point, except that they're operators. And now what you really have here is the endpoint function, and you can say, just to make your life easier, that it's perhaps a Gaussian state. So then you only need the 2-point function, because you know for a Gaussian state, the nth moment, or the 2nth moment, is given by the second moment. And so now you have to say somehow what you mean by that there is a regular initial state. And that kind of notion has, has evolved, has been a very important question in this whole subject, in a sense. And there is now a consensus that, there's a lot of evidence for it. What this means to be a regular state is at the level of the 2-point correlation function. That the 2-point correlation function, you can't say it's a smooth function, because it just doesn't want to be a smooth function in any state. But you can say that the singular part is determined entirely in terms of the geometry. And then there is a part which is just determined in terms of the state. And that part is supposed to be smooth. So it's not, the whole thing can't be smooth, just from the Heisenberg uncertainty. But there you can kind of suitably isolate the singular part, just knowing the local geometry. So it's like the Green's function of a Laplacian on, let's say, some Riemannian manifold. So the coincidence limit of the Green's function is kind of, the singularity is determined by just the local geometry, but the smooth part is determined by the boundary condition, and it's global in nature. It knows about the entire Riemannian manifold. So this is the kind of similar. Okay, so the main result is concerning a quantity called the stress tensor, which is now also an operator. And this operator, we can't, this has infinite fluctuation, so we have to think of its expectation value in this kind of smooth state. And what we obtained is the following theorem, is that this stress tensor, this flux of stress energy, blows up, just as Penrose said, on the Cauchy horizon with a V minus 2 inverse. But then there is a state-dependent thing which goes in this way. So our result is really a combination of what Penrose said and what the mathematicians say. So it's what Penrose said, in the sense that it's the quantum part of this thing which behaves really in this way, and the state-dependent part behaves just like a classical solution. And there is an overall constant here, which just depends on the black hole parameters and not the state. So our conclusion is that the determinism is restored because quantum fluctuation, so this part here is really proportional to h bar. So if you put h bar in somehow, then there will be h bar in front of it. This one. And so you see, if c is bigger than 0, the sign, then if you're an observer and you approach the Cauchy horizon, you become a spaghetti. But if c is less than 0, then you're, I don't know how these hideous torture instruments in the Middle Ages are called in English, but you're torn apart when c is less than 0. And what the value is of c does not follow from this theorem, but you have to have a way to calculate it. And that's what we also did. Now here is again the space-time diagram. So instead, let's not think about Bob, but a galaxy. So a galaxy going through the Cauchy horizon would be either compressed if c is greater than 0, or it would be stretched if c is less than 0. And now we found also a way to evaluate c, and it's a function of the black hole parameter. So there are basically three. There is the charge, the mass, and the cosmological constant. So you can only vary one at a time to draw if you want to plot like this. But you see, it doesn't matter what these values are, but you see it's both positive and negative, depending on what the charge to mass ratio is. So for a so-called extremal black hole, it tends to be negative, and so you become torn apart. And for a more mundane black hole, it's more positive, and you're the spaghetti after crossing the Cauchy horizon. So here we varied also the mass of the field just to be sure that there was nothing strange there. Okay, so behind this is actually a theorem, and I don't want to perhaps spend too much time on explaining what the theorem is, because I have to explain what this quantum stress tensor is and all this before you can really say mathematically what this result is. But so perhaps the interesting parts of this are that this theorem is really about the Green's function in the end, the two-point function of the state. Now, I don't really want to start with Hilbert spaces. I could, but a better approach is just to think of a state as the label of all possible two-point functions having certain properties. And those properties are that, well, most basically, this is a distribution. It satisfies the wave equation because the field does. It's of positive type because the Hilbert space has a positive definite inner product. There is a part involving the imaginary part of this, which has to do with the commutators, and this relates then to the advanced minus retarded propagator. I've put an H bar here. So here's the quantum part. You see H bar comes in. And then there is this condition about the state being initially regular. And that's where some interest, that's where that's best formulated in terms of not this condition, but in terms of a condition on the so-called wavefront set. So the wavefront set is a concept that was invented by Hermander and I guess others. And there is a theorem in this subject that this condition on the wavefront set is equivalent to this kind of form of the Green's function with a smooth remainder. And then once you know that the remainder is smooth, you can define the stress tensor as suitably derivatives of this smooth remainder at on the diagonal. And then the theorem is really about this piece. And it's again that there is a quantum part which has a universal singularity, and it only depends on the black hole parameters. And then there is a, in quote, classical part, which is in a certain Sobolev space, just as the mathematician said. And there is a part where you want to compute this coefficient C to know whether you are going to be the spaghetti or whether you're going to be torn apart. And there are two, this is a kind of a scattering type problem for a radial Schrödinger type equation on this background. So you have a wave equation initially, but if you make a separation of variables, ansatz, you can perhaps see in your head that this could lead to a Schrödinger equation, a radial Schrödinger equation. And actually you have two, you have the black hole interior and the exterior. So it's two subsequent scattering problems. So waves scattering into the black hole, and then once they're in the black hole, scattering through the one or the other Cauchy horizon. Okay, so let me summarize the results of this talk, or maybe let me make a few more comments on the mathematics involved here, because after all, you're a mathematical physicist, and maybe that's what you care more about in the end, I don't know. So the crucial there are two ingredients, so to speak. The result really is this one here. So there's one ingredient that is telling you that this is in a good Sobolev space. And this is involves the full machine of this advanced versions of this micro-local analysis, which go in the end, you have a black hole space-time and classical particles will learn about the geometry. And you know maybe that the micro-local analysis is a kind of a mathematical version of the semiclassical approximation. And so the semiclassical approximation then knows about the Hamiltonian structure of orbits, classical orbits, geodesics in this space-time. So there is a very powerful mathematical machinery that relates these properties of the Hamiltonian phase space to decay properties of the wave equation that's been worked out by Melrose, Varsi, people from this school, of course. I'm sorry, Hermander himself, Duistermatt, I can't. So there's even a book on the Söstrand. There are many names associated with it, and Hinz and Varsi basically tweaked this technology to the extent of being able to say something really in this concrete situation. And what we do is we massage the situation in a way such that we can infer statements about this classical part. And then there is this quantum part, which really saves determinism, and that involves really a calculation or an expression for this constant C. Well, there is also the whole business of setting up states. So there's an intricate relation to ideas of micro-local analysis and how singularities propagate and how they quantitatively propagate. I can't go into this, but there is a very concrete part of this calculation where you need to actually determine this C and to make sure it's not zero. And then that's this scattering problem, which also is very interesting mathematically, because the Schrödinger operator is a 1D operator, is related to some famous second order ODEs in mathematical physics called the Hoin equation. It's related to many interesting things that could be explored in this context. But in the end, it just gives you a machine to compute a C. So let me summarize what you have perhaps learned, or what I'm claiming. So my claim is that quantum effects rescue determinism inside black holes. So there is an issue, but it's rescued by quantum effects. And there is a corollary, which is that quantum effects are much larger than classical effects inside the black hole or at the Cauchy horizon. So we're all used to quantum effects being really a tiny correction most of the time. But here it's opposite. They're huge. The classical effect is small. The classical effect is in this nice Sobolev space, and the quantum effect is the terrible one. Of course, outside the black hole, it's the other way around. So at the event horizon, quantum effects are very, very small, and classical effects are big. So inside black holes, at least at the Cauchy horizon, quantum effects dominate, and they rescue determinism. At least that's what we claim. So thank you very much for your attention, and I guess I stop my slides here.
Well, thank you very much. So are there questions?
Well, I have one. How can quantum effects rescue determinism if quantum mechanics is non-deterministic by itself?
Oh, okay. So quantum mechanics is deterministic, first of all, insofar as the Schrödinger equation is concerned, and the correlation functions, and in particular the expectation values, they are basically determined by the Schrödinger equation. So that's also deterministic, just as the Schrödinger equation of quantum mechanics is deterministic. So the indeterministic part, of course, the quantum indeterministic part is that you have always, not just inside black holes, is if you have said that, okay, an observable has such and such an expectation value or variance or seventh moment, what are you actually going to measure? If you measure only once, you don't know. So, but you know that if you do the measurement many times, you will build up statistics. And in this sense, again, that statistics, the odds are again determined deterministically. I mean, that's the usual thing. So I think there is no contradiction. I think the issue with determinism in black holes is much more severe, because even without quantum mechanics, you have a big problem.
So is it really true that galaxy that approaches this Cauchy horizon, it shows quantum properties? It's not anymore a classical object.
So what's affected is the quantum fields create a quantum stress, a stress tensor, an expectation value. And of course, you have to say that this stress tensor will be affecting the metric in turn, because it's going like any stress energy, as you know, as a relativist, appears bend space. So you would have to take that into account. Of course, the galaxy is a classical object, so the stars would just be moving on basically geodesics in this space-time, though, which has received these enormous corrections due to the quantum effects. Yeah.
So Stefan de Bier has a question.
Yeah. How close do you have to get to this horizon for the quantum effect?
Oh, yes. So that's good. Very good question. So you can see it the following way. Maybe I should share again. Here, maybe I should share this again. Let's see. So here is my main formula, but so there should be a h bar in front, first of all. So C is like, say, an order one thing, but then there is h bar if you put if you leave it, if you don't set it to 1. And then this stress tensor would appear on the right-hand side of the Einstein equation. So there should be G Newton in front of everything. So you have G Newton times h bar in front of everything, and that's basically the Planck. So it sets this to be, so it's a Planckian time, or a Planckian time away from the Cauchy horizon that you would see this effect.
That's pretty late, I guess.
Better late than never, I would say.
Yes,
I have another. Oh, yeah, I have another question. I think there is a fundamental problem trying to couple quantum mechanics with the classical system. At the end, if you take it too seriously, you run into contradiction. So does this issue bother you, or not at all?
Well, I do.
I can explain the difficulty if you
No,
don't
I
know
understand
what I mean.
you're talking about. I don't. I personally, clearly, if you have an expected stress energy, it should appear on the right side of Einstein equation. I mean, how is the metric supposed to know which part of the stress energy is coming from classical fields and which from quantum? So that's one thing. Now, what is the correct, really mathematical formulation of this fully coupled system, and whether it has unphysical solution is certainly a relevant question, but there can be no doubt that if you have an enormous stress energy density created by quantum fields, for example, if you collide them inside CERN, this will affect the space-time curvature. It's just some part of some sort of stress energy. But exactly how you set it up mathematically, indeed, you're right. I think that's not completely clarified. I mean, there are, in the case of electrodynamics, where you say maybe you're only interested in stationary states, and now the stress tensor is the current, and the metric is the electromagnetic field. there you can make a satisfactory theory. You know, in physics it's called density functional theory, and I think Mathieu Levin has results on this. I mean, there are instances where you can make a sensible theory out of this.
Thank you.
Other questions?
I have a question. As far as I know, the stress energy tensor is ambiguously defined as that there is a freedom of renormalization. So which one you choose in your theorem?
It doesn't matter, because the ambiguity are just curvature terms, and the curvature is just smooth on the Cauchy horizon. So it doesn't matter.
Okay.
So you could always, if you add a smooth term or to this, it doesn't change anything. But you're right. If you were, if you have to do, if you do the calculation at the event horizon, so as to calculate how much radiation, Hawking radiation is coming out, then because that's very, very small, you have to be careful about this. But here not.
Thank you.
Other questions, somebody?
Yeah, I want to understand what precisely you have done here. So did you consider Gaussian field theory on curved space-time? And
yes, indeed.
And
so
then you use this energy stress tensor of this field expectation value.
Correct.
I don't. So yeah. Okay. So,
So
that's
the theorem is if you start out with a Hadamard state, which is a state satisfying these 5 properties initially, which is the quantum analog of a smooth initial datum, then the theorem is that the quantum stress tensor has this form always at the Cauchy horizon, where this is a non-zero constant generically, some part which blows up and some part which is member in a certain local Sobolev space, and therefore less singular than this.
So in this case, of course, space-time feels this quantum field.
Yes, okay. But the theorem is about the correlation functions, if you like. So it's a theorem about correlation, how the correlation function behaves near the Cauchy horizon. You can think about it this way.
Okay.
So the operator is not what you're looking at. You look at the correlation function and actually just this one point correlation function. But you could look at other correlation functions with similar results.
Thank you.
Okay, Stefan de Bièvre has raised his hand.
Yeah, I have another question. If you you mentioned in the beginning, if you look at a nonlinear field theory on a curved space-time, could that change something? Could the nonlinearities?
Yeah, I mean, in fact, I should say the mathematicians, at least some of them, have looked at, really they want the Einstein equation. So, you know, they don't want a silly scalar field, but they want the full nonlinear Einstein equations, which is a kind of wave equation too. You know that. And they certainly have looked at nonlinear things, but in a way, if you know that there is a singularity and it's bad, then the nonlinearities are not going to make it any better, most likely. They were really concerned with the opposite, because in the classical case, I explained that the singularity is very weak at the linear level. And then you can, of course, ask, well, if there are now nonlinearities in the field equations, could they somehow become strong? And they, in their game, therefore, is the other way around. They want to show that they can't. And so, for example, Penrose and Luke show that even with nonlinearity is still continuous. But, you know, so here it's the opposite. We show that even at the linear level, it's already bad, and we're happy to see that. And then we don't even bother to show that at the nonlinear level it's worse, but it has, you know, it would have to be, but okay, it's not something that's easily done.
If I may follow up, the dominant effect is quantum here, so the question is more, could it affect the quantum term?
Yeah, I don't think so. I mean, of course, the problem is you don't really have good control over nonlinear quantum field theories other than in perturbation theory. And now in perturbation theory, there is now a machine which at least shows that the correlation functions of the interacting fields themselves are well defined. And you could look at these, but you see, if it's a perturbative construction, so the correlation functions are formal series with highly non-trivial terms, but there are formal series in the coupling. So if a field gets really big, for sure, the nonlinearity is no longer a small perturbation, and you just wouldn't trust this.
Okay.
So at CERN, you have scattering, and so in the asymptotic regime, sort of the fields, the quantum fields, whatever, are very small, and that's why you can. Oh, that's certainly one reason why you can apply perturbation theory. The nonlinearity is small, but if here it would be big, and so we couldn't apply perturbation theory, and then I don't really know what to do.
So there is a question by Vincent Blasi.
Hello, just wanting to say there's a question in the chat.
Should I look into the chat? Okay, though separately.
Let me check the chats. Douglas Lanholm, what could be expected from quantum gravity effects?
Well, quantum gravity, I don't know. I don't know. I can't answer it. I don't. I mean, you can apply this analysis to the quantum fluctuation of the metric. And although we haven't done it, I'm expecting the result to be the same. But if you want to a fully non-perturbative formulation of GR is beyond my expertise.
Further questions? If not, thank you very much, Stefan Hollands. Let me stop recording.